Welcome back. Talking about potential energy and energy conservation. I wanted to, in this video, show you how potential energy relates back to the force that causes this conservative force. Any conservative force we can associate a potential energy with. But remember, potential energy, the way we defined that potential energy changes, was in terms of an integral, right? It was related to work done minus the work done, but work is an integral of force with position. So if I want to undo the integral to get what's the force from the potential energy, I do derivatives, right? Anti-integrals. So I undo those integrals, but for us, we want to make it as easy as we can. If I know that forces are really vectors, and it turns out there's this cool operation that you can do in vector math called the gradient. That's that upside down triangle with the vector sign over. It's called a del. I'm trying to get Del Taco to change their signs to have that symbol and a taco, right? Just for math education, it'd be good for us. Join the crusade. But that gradient of the potential of some associated with some conservative force can give me the force as a vector. But remember, for us, we want to simplify this a little bit. Our forces are really, we're going to write in Cartesian coordinates, right-handed coordinates. So I'm going to have an x part I hat direction plus y part j hat direction plus z part k hat direction. How do I find those x, y, and z parts? Well, I take partial derivatives. If you haven't done partial derivatives before, don't worry, they're even easier than regular derivatives. When I do a partial derivative with respect to x, everything that's not x gets treated as a constant. We'll see an example in a minute. Same thing. Partial derivative with respect to y, everything that's not y gets treated as a constant. Partial derivative with respect to z, everything that's not z gets treated as a constant. We'll see it in an example at the end of this video. So we want to relate these things to equilibrium. Now remember, equilibrium was when force equals 0. So equilibriums would mean that the equilibrium would mean force equals 0. So that would mean that the derivative with, right, x position, I could find positions for x, whenever that minus the partial derivative with respect to x equals 0, I'd have an equilibrium position in the x direction. Same thing with y and z if I wanted to do 3 dimensions. We're going to stick with one-dimensional stuff. But I can kind of recognize from calculus class, now wait a minute, I remember taking derivatives of stuff, setting it equal to 0. What were you doing? You were finding maximums and minimums, right? Maximum, minimum, maximization, minimization problems. But there was one other thing you had to do. You had to take a second derivative. That's what we're going to do down here. And this is really just a difference in jargon. For calculus class, you would take that second derivative, evaluate it at the maximum or minimum point when x was equal to the maximum or minimum. We're going to call those equilibrium positions, not the position of the maximum or the minimum. We'll just call them equilibriums. So I set that, I find that by setting the first derivative equal to 0 and solving for x. Then I can take the second derivative, plug in where x is one of those equilibrium or maximum minimum positions, and evaluate. If that turns out to be greater than 0, that's a stable equilibrium. So here I've got a picture of a block on a spring, and above that there's a graph that shows the potential energy of the block on the spring as a function of x. Notice right there in the middle it's 0. X equals 0 is where the potential energy is clearly the lowest, right? That's an obvious minimum, right? And I have that upward curvature that you may have talked about curvatures in calculus class. That upward curvature shows me where the minimum is. I can look at a potential energy graph and see, oh, the minimums, those are stable equilibrium points. And the way to think about that is that if I displace the object a little bit from that point, it'll try to get back to that same lowest potential energy point. That is the nature of stuff in nature. It wants to get to its lowest energy state, the lowest it can. And the lowest this can is to have the spring neither stretched nor compressed, just relaxed completely, right? So we express these things mathematically with derivatives. We're going to get to an example to explain more. But it turns out that in addition to the stable equilibrium, which corresponds with our mathematical minimums, stable equilibriums find the mathematical minimum and prove that it's a minimum. There are also two other kinds. Of course, we know there would be maximums, right? Maximums correspond with unstable equilibriums. If it's unstable, that second derivative evaluated at the equilibrium point will be less than 0, or a downward curvature, right? We're evaluating these curvatures. In an unstable equilibrium, if I move the object just a little bit away, it'll continue to slide away forever. So you can imagine maybe this is a hill or something, right? And I have a block on top of the hill in that graph. If I move it off the top of the hill a little bit, my nice frictionless hill, it slides down, it goes away from the equilibrium position forever and keeps going away. That's unstable. So it's only in equilibrium at one point, and as soon as I displace it, it's going to move away from that and probably never get back there. So that unstable equilibrium. Turns out there's also a third kind. What if there were a region where there was 0 curvature or a nice flat piece? That's neither a maximum nor a minimum in math class. For us, we call it neutral equilibrium. Neutral equilibrium when x equals 0. And you can see right in this area right here, that's pretty flat. If I were to move an object away from that equilibrium position, it would still stay in equilibrium in its new position. I have sort of this range of things where the curvature is 0 and everything of the potential energy function, everything would stay cool. So those three kinds of equilibrium are things that we want to look at: stable, unstable, and neutral. And of course, we want to be able to find equilibrium positions. Here's an example. We're just going to work through this as the way to find this. And remember, this corresponds exactly with finding maximums and minimums, doing maximization, minimization problems in calculus class using derivatives. The only difference is what we call them, right? We find the positions of these maximums and minimums, and we call those equilibrium positions. Then we evaluate the curvature and with that second derivative, and we judge whether those equilibrium positions are stable, unstable, or neutral. So here's a potential energy function right here as a function of x. We'll make this easy on ourselves and just do x, right? So I could find the force in the x direction by taking minus the derivative of that with respect to x. So remember, if I do this, I get, let's see, that would be 3x squared minus 3, and then the derivative of the constant 1 is 0 at the end, right? So I take that, and I'm going to just put my minus sign that I almost forgot. I'll just put it out front. What I really want to do to find the equilibrium positions is to set this equal to 0, but minus 0 and positive 0 are the same thing. So I'll just say 3x squared minus 3 equals 0. A little bit of math later. X equals, let's see, the square root of 1, which is just 1, but plus or minus, right? Plus or minus 1. Plus or minus 1. That's it. So I actually get two equilibrium positions, plus 1 and minus 1. We could see this if we looked at a graph of x cubed minus 3x plus 1. Try that. Use your fancy graphing calculator, or go to Wolfram Alpha or Mathematica. Use some graphing software online and look at the graph of this. You're going to see bumps at plus and minus 1 that are going to correspond with these maximums and minimums. So there are my equilibrium positions, plus and minus 1, right? Well, now I want to evaluate them. So I'm going to make my note up here, x equilibrium positions plus and minus 1, right? But I want to evaluate, and what I need to do is take that second derivative. So the first derivative was 3x squared minus 3, right? Well, I take another derivative. Let me write that down. First derivative, make sure I get it right, 3x squared minus 3. Yeah, so now I take another derivative and I get 6x, right? And that's it. I want to evaluate this. So first I want to do at x equals plus 1, the first equilibrium position. That's going to be plus 6, which is greater than 0. So that means x equals plus 1 is stable, or it's a minimum, right? And then I evaluate at x equals minus 1, gives me minus 6, that's less than 0. That gives me x equals minus 1 as unstable. And make sure my 1 actually looks like a 1. That's how we do these potential energy back to force problems, evaluating equilibriums. This is a great shortcut. Instead of having to do all of the force stuff that we did before, all of Newton's laws, sum up all the forces, set them equal to 0, try and find at what position does this happen, I just associate with these potential energies. If I have a nice conservative force, I can associate a potential energy with it. I can find equilibrium positions for these potentials, which is super duper handy. There's some great examples that get used in some more complicated physics, chemistry, like the Leonard-Jones potential about atomic bonding. It's where is the potential minimized between two atoms that are bonding together. That minimum position, distance between, gives you the bond length, the average bond length. And you find it minimizing stuff with derivatives. Really not terribly difficult, and really an amazing development. So try some of the problems in the homework involving this. This is about as complex as we'll get. Remember, I might add in some extra dependence on y and z and other things. Try the homeworks, put up questions in the discussion section, in the discussion forums on Canvas, and we'll address them there. I'll see you in the next video where we'll do some more energy conservation problems.